Hello again and welcome back to my channel. Today we'll talk about torch.DistributedDataParallel or DDP. Here is the series progress so far. So we've started with just mathematical explanations about what is data versus model parallel. And we've seen that data parallel is the easiest, it doesn't require changes in model code. Then we've looked at a module called data parallel from PyTorch that lets you implement that in exactly one line of code, which is pretty easy, but it had two drawbacks. So one being that it only works on one node, so one node, multi-GPU setup. Second one being that it's actually a bit slow because of Python interpreter lock. Then we've talked about torch distributed, which is a low-level communication package that is used in everything else that happens nowadays in distributed training. So all the major frameworks of the major companies actually rely on that framework to do distributed training. And what it does is that it allows cross-process communication, which fixes both the problems outlined above. So now we can launch multi-nodes, multi-GPUs, and it's not suffering from global interpreter lock. And today we'll look at torch.DistributedDataParallel or DDP, not to be confused with just data parallel. So the difference here is in this distributed prefix, which is the PyTorch framework to actually launch data parallel training. And here's the plan for today. So we'll start with a simple training example on MNIST digit classification, and then we'll basically see what we can do to apply torch.DDP to that, to parallelize our training. As we'll see, it's now a bit more complex than just data parallel. So apart from the actual wrapper, you'll also need to do distributed setup, launch multiple processes. In addition to that, you'll have to pay close attention to what parts of the data you feed to each process, and that's usually called distributed sampling. And in the last part of the video, we'll actually implement something analogous to torch.DDP by hand using just torch distributed. And we'll start with a simple example training on MNIST digit classification dataset. So I'm not going to write anything new here. I'm just going to rely on an example from the PyTorch GitHub repository for MNIST training. So in here they have a simple convolutional neural network with a bunch of convolutions, dropouts, and then fully connected linear layers to basically take in the image of a digit, so a simple image in black and white, and pass that through convolutions, through some fully connected layers, and then output log probes for one of the 10 classes for 10 digits. And here is the simple train for loop. So this is just bare PyTorch. We do not rely on any framework for training. So we just iterate over the data ourselves. We put it on a device, which might be a GPU if one is available. We use optimizer by hand. So we call zero-grad before everything, and then we call optimizer.step after everything. We call the actual model to get output probabilities for each class, for each example in a batch. We calculate the loss, which in this case is negative log likelihood loss, and then we call loss backwards to actually compute the gradients. In addition, what we do here is we report some test metrics and train metrics. So here's the code for train metrics. We report that every once in a while. And then we also have a separate test function, which pretty much does the same, but without actual training and gradient computation. And we have a bunch of parameters to basically set up what is the batch size, what is the learning rate, and so on and so forth. So by default, we are going to use CUDA if it is available and it's not explicitly disabled by user. So we're going to initialize device as just the string CUDA. And here we have our data loader, data set, and so on. So for the data loader, we pass in the arguments of batch size. And in addition, if we do use CUDA, we also pass in num workers, pin memory, and shuffle. So num workers basically means that I'm going to assign an extra CPU to load the data, which will happen sort of in parallel to the actual training. Pin memory is a special thing which transfers the data that we've just loaded into a special CPU location called pinned memory, which makes it easier to transfer that to a GPU, and then shuffle the examples, which is the standard for training. So the actual dataset is just datasets.MNIST, which does everything for us. It just loads it from the internet, saves it to disk for caching, and then just provides us with examples. And also have these data loaders, which basically handle composing different examples from the dataset into batches and iterating over these batches. So I have my model, my optimizer, I will have a learning scheduler here, and this is the for loop for the actual training that iterates over epochs and calls this train function that we've seen above. Finally, we put the model to device, which in our case is going to be CUDA, which the literal string CUDA, usually if you don't have any distributed training set up, it will just mean one GPU. And this is how we are going to launch it. So in here I have exactly the same script. I called it train.py, and I can just call it as Python train.py. I also want to prepend it with the Unix time command to actually measure how long it takes to train, because we are going to be experimenting with distributed training, so we want to see how much does it actually allow us to speed the training up. I can look at my NVIDIA SMI. You can see that I have 8 GPUs on my node. Only one of them is being used by default. I can see that the actual GPU usage is not that great because we use naive for loop for iterating over data, so obviously that is not going to be insanely effective, and our actual model is so small that it's just unable to load the GPU on 100%. Nevertheless, one thing you can see here is that only one GPU is used. So let's wait until the training is done. So the training is done. We can see the final accuracy, and we can see that it took 193 minutes with 3 seconds, which is a little bit above 3 minutes. So let me just save all of that into a text file, because we are going to compare our launches by accuracy and by speed. So now let's look at this and try to implement just the simplest torch distributed data parallel. So I'm going to import torch distributed, and one thing that we'll need to do is we're going to wrap our model in torch distributed data parallel, or DDP. So you can see here that it already expects some sort of device IDs, and the cursor suggests that I should just get that from torch distributed, which sort of means that by this time it has to be initialized. Just for the sake of experimentation, let's just delete this one for now, and I'm going to just try to launch it like this and see what happens. So I've wrapped my model in distributed data parallel. I'm not doing anything else. I'm just going to launch my script again and see what happens. So quite as expected, the module itself complains that in order to work, it actually needs to have the process group initialized, which is what we've talked about in the previous video. So let's add the code for that. So I'm going to just copy paste the function that we've used in the previous video, which initializes the process and does a bunch of print statements. And let's call this init process function somewhere here. Right, so now I'm doing my initialization, which means that I also need to launch several processes at once if I need to do the actual training. So one way to do that would be to use torch run, but you can also just launch several processes by hand, or you can also just use Slurm or any other cluster setup thingy. So we can launch it using torch run. I'm asking for 2 nodes. And let's see what happens now. So you can see that the process group is being initialized, and then it fails with an error that says duplicate GPU detected. So this is the second problem that we'll need to solve. So remember, we've placed that on a device where device is just the string CUDA, which by default means the first GPU. Well, lucky for us, NCCL automatically discovered that we're actually having two models, two processes trying to compete for the same GPU, which is not really very good. Even if it would work, the GPU will basically have to switch back and forth between the model, which definitely is not going to speed things up. So the easiest way to fix that is just to append this suffix of 0 or 1, depending on what the current rank is. And here, since I've already initialized my process, I can use this torch.DistributedGetRank function to automatically get my current rank. So now this will work. Let's restart it and see what happens. So it actually started training, but we still have a problem. And the problem is that we still use our default data loader and data set, which, as you can guess, doesn't know anything about torch distributed. So the way this works is we now launch two processes in parallel. Each of them knows about their rank. We pass in this information implicitly to the model by wrapping it around in distributed data parallel. We pass in this information to the device like this, but we do not make our data loaders aware of what is going on. So what will happen is each of these two processes will read exactly the same data, which is not really what we want. We want them to get different data. And the easiest way to fix that is to use the specialized sampler from PyTorch. So here's how we can do that. So I'm saying that train sampler is equal to torch utils data distributed sampler, and then I just say that I want train data loader to use this sampler. So what will happen now is this sampler is now aware that we're doing distributed training. It knows the rank of the current process, and what it will do is it will basically take only the half of all the examples we see. And the process with rank 0 will take one half, the process with rank 1 will take another half. So now the data loaders will automatically just fetch unintersecting segments of the data for us. So now this should be correct. So let's restart our training and see what the accuracy is. So I'm restarting my training, again asking for 2 nodes, see if it works. Okay, so here it says that operation is mutually exclusive with shuffle. Let's fix that as well. Let's just remove this shuffle here, because sampler is going to do the shuffling for us. So the training is going. Let's check what is happening to our GPUs. So now we can see that the first 2 of them are used, which is what we expected. And let's wait until the training is done. So it is done. We can see that. Let's just copy the results here. So we can compare results with the previous launch. So previous launch took 2 minutes. Yeah, actually I told you wrong. So this time is for basically CPU time, which is 100. Which is more than the actual real time that passed, because we use more than one CPU. And so the previous run took 2.5 minutes, and the new run took about 1.5 minutes. So it's not quite twice the increase in speed because of overhead, because of communication, because our code is definitely not optimal, but still it's quite an improvement. But the worrying thing here is that the actual accuracy is now worse. So before that we got 9,917 examples correct, and now only 9,904. And the reason for that now is quite subtly the batch size. So if we come back to our code, we have our batch size, which we can actually pass in through the arguments. We have our data loader, into which we pass our batch size as well. But now that we are dealing with distributed training, we now have two properties that can be called batch size. So we have global batch size and we have micro batch size or per device batch size. So this batch size that is being passed around in the arguments is now per device batch size, because every device initializes its own data loader and says to unite examples into batches of this size. And now, since we have several processes running in parallel and each of them communicate to each other and exchange gradients, our effective global batch size, which is the thing that actually affects convergence, it is now 2 times higher because we use 2 devices. So we need to fix that. So the easiest way to fix that is just to automatically adjust that based on our current world size. So I'm going to just say that I'm going to divide my batch size by world size, and also I'm going to assert that it's actually divisible. Right, because if someone asks for batch size of 63, that's going to be unexpected. So let's just protect ourselves from that. So let me restart the training with the same arguments and see how it goes. And the training is done. We can see new results. Let me copy it to the same page. The time is roughly the same, but now we are back to our normal quality. So let's sum it up. Torch distributed data parallel, what it takes to parallelize your training with DDP. First of all, it's the easiest part. You just wrap your model in torch.DDP. In addition to that, you will need to initialize your distributed process group, basically calling some code from torch distributed and providing it with total world size, rank, master address, and master port. You'll need to launch several processes somehow, either by hand or torch run or slurm or by any other means. You will need to take care of your data. You'll need to make sure that every process is reading independent data sample, which is easily handled by torch distributed sampler. And finally, you will need to adjust batch size, because now your batch size is your micro batch size, whereas what you actually are interested in for convergence is global batch size. Finally, let's talk about how we can implement our own version of DDP by hand. So I'm going back to my train.py code. I'm going to remove just this DDP wrapper, and I'm going to leave everything else in place. So I still want to have distributed sampler, I still want to have my distributed setup, but I want to implement the actual training in distributed setup myself. So what has to happen? If you recall from our previous videos, this is the example diagram of what is happening during data parallel. So basically the model call remains unchanged, the gradient computation step remains unchanged, but then we need to have this cross communication between devices after all the gradients were computed, and basically exchange the values and average them out across devices. So there's no actual gradients being passed around here. So we know that the gradients get computed when we call loss.backward, and when we call optimizer.step, they are actually being applied and they change the model weights. And then at the beginning of the next iteration of this for loop, they're going to be zeroed out with this optimizer.zeroGrad function. So let's go to a Jupyter notebook to test everything out. So here I have basically the copy of all the same code we have before. So I have imports, device, transforms, datasets. I can load my actual image and actually see how it looks like as a tensor. So it's a black and white 28 by 28 image. Then I initialize my arguments, string data loader, network, model optimizer scheduler. I will not actually do the training here, but what I am interested in is just calling a model on a single example of data. So I'm going to iterate over train loader. I also need to put the input data to the device and call the optimizer zeroGrad. So we can access the parameters of the model using model.parameters. And in our case, this length of the parameters is 8. So if I come back to the model, we actually have 6 fields. 2 of them don't have any parameters, and the rest 4 convolutions and fully connected layers, they have the actual matrices, the kernel, and the bias. So 2 per each layer. So 4 layers, 8 in total parameters or parameter groups. We can look at an example of such a parameter by just taking the first element of this list. So this happens to be a kernel for the first convolution. So it projects a single color into 32 dimensions, and it's a 3x3 convolution. And we can actually access the gradient as param.grad. So by default it is a none, which means it's not even going to print anything. So to understand that something actually has happened, you need to type in param.grad is none, and it will tell you that it is true. It is indeed none. So then when I actually compute the output of the model and call this negative log likelihood loss, and then call loss.backward, I can check again that param.grad is none is now false. So I actually have some gradients computed, and they are stored in exactly the same place as the parameters themselves, which is quite a nice default by PyTorch library, because I honestly don't know when and where would you want to apply a parameters gradient to some other tensor, but you still can do that because you can still access this param.grad. But normally you would just apply parameter gradients to these parameters themselves. And param.grad is a matrix with the same shape as the parameter itself. So in our case that's 32 by 1 by 3 by 3. And we can again make sure that once we call this optimizer.0grad, this param is back to none. So now we have to insert some sort of parameter gradient exchange function somewhere here. So I'm just going to call this one average gradients and just put it after we've called the backward, so after the gradients were actually computed and before optimizer.step. And this is how my average gradient function will look like. So it takes in an argument of model, and then I iterate over all the parameters of the model, and I call torch.DistributedDataParallel, which will basically sum the gradients from all devices. It will sum it up and put it back into this param.grad tensor. And what I also do after that is I'm going to divide that by total world size. And the reason I want that is because typically when we talk about loss, we average loss across examples. So in our case, with effective batch size per device of 32, before we were doing this average gradients, we would average loss across 32 examples. Now we got our gradients and we exchange them, which means that gradients are like twice higher. And to bring them back to the average that we expected, we divide by the world size. Not all losses are doing that. Some losses actually expect the total value to be the sum of losses across all devices. So this code will only work for losses that expect averaging out. And so the only actual torch distributed call that we need here is all reduce. So before this call, my local version of parameters just contained my version of gradients for current device. After this call, it will get averaged out across all devices, which means that my local copy of gradients now has information from all the other devices. And then when I call optimizer.step, I actually apply these gradients to my model. So now I can still call my script like that. And let's see how much time it will take and what will the final accuracy be. So I can check that both GPUs are still being used, so that's good. And let's wait until it's finished. And the training is done. Let's copy the results. So you can see that the accuracy is still the same, but now we are slightly slower. So let's discuss why that is. And so the reason that our naive code might not be optimal is that, first of all, we iterate over all the model layers, and then we do the communication for each layer separately, which means that, you know, communication for the second layer will not start until we finish with the communication for the first layer. So we have a bunch of barriers one after another, which is not really good. Second, we also compute all the gradients before even starting to exchange information. And again, this can be optimized. So one thing you can do is when you do backprop, as soon as you are finished with computing gradients for the last layer, you start exchanging those gradients for the last layer, while the gradients for layers before that are still being computed. So you sort of overlap the exchange of gradients and the computation of gradients, which again helps you speed things up. So let's go over all that just happened with data parallel, because there are a bunch of things that are not that obvious. So we've started a bunch of processes, we let them connect to each other and communicate, but each process reads its own portion of data. And it's up to the user to make sure that each process actually reads different portion of data, otherwise you'll mess up your conversions. And this is quite a tough problem to debug, because you will not see errors, you will not see that anything is wrong. The only thing you will see is that your final accuracy is not as high as you might have expected it. Each process holds a copy of the model by basically loading the model from pre-trained, from Hugging Face, as we did it. Then each process computes its version of gradients on its own portion of data. Then we exchange gradients between processes, and this is the only actual step that requires cross-communication between processes. And then something interesting happened. So then we need to apply the gradient. So we have the gradient after all the exchanges, after we've communicated to other processes. We have to apply it to current model weights, and each process does that independently. And this might actually yield slightly different results on different processes because of stuff like floating point computation and so on. Generally, it's not a big problem, but just be aware of it. So what will happen is we have now several versions of the processes, each applying the same version of gradients to the same model weights independently. And so we rely on that process to always yield the same result, which is not strictly true. So sometimes you'd have epsilon difference in what the final result is. The same goes for the state of the optimizer itself. So L1, L2 momentums for Atom. Again, they start from the same point, but then each process applies the same difference, but independently. So you might arrive at slightly different results over time, especially if the training is very long. And this is generally quite an popular case for distributed training, where you rely on processes to arrive at the same result while executing different code. So it's important to take care of stuff like seeds and random number generation so that you actually know that they will have the same data. So this is it for today for our first practical data parallel example written in bare PyTorch. In the next video, we'll talk about PyTorch Lightning and how to set up the same MNIST digital classification model with PyTorch Lightning and data parallel training. See you soon!